I'm home now, so I'm trying a new setup for video taking with this little whiteboard that I took home from my office. All right, so let's pick up with 8.4, which is magnetic force on a current carrying conductor. So the fact that moving charges experience a magnetic force in a magnetic field was first discovered because there was a magnetic force between two wires that each produced their own electromagnetic field and exerted a force on each other. So we know already that moving charges experience a magnetic force in a magnetic field. So let's look at extending the math for that to cover moving charges in the form of current in a wire and look at the force that a magnetic field will exert on a wire. Okay, so I've drawn an image here of a uniform magnetic field I've just chosen into the page, and then we have a wire in that field with current sent up the wire, and the charges in that wire will move with a drift velocity Vd. Okay, so just using the constant speed formula, or constant velocity, that Vd equals distance displacement over time, we can define L. This L vector is the displacement along the length of the wire. So it's still displacement, it's used as L to indicate that it's in whatever direction the wire is. So we have displacement over time, and then I can rearrange that to have time is that displacement over the velocity, the drift velocity. All right. I want to do this so I can rewrite the equation for the magnetic force on a moving charge to show magnetic force on a wire. So then our equation for current is I equals Q over delta T, the charge per unit time. And what I want to do is just plug in delta T here. So I'm plugging in delta T right in this denominator, which means this is L over V, and it inverts since it's in the denominator. And then this can be written as IL equals QV. Drift velocity if you want to label that. Okay, so then before we had FB equals QV cross B. And the charges in this case are moving at that drift velocity. And look, this QV can be replaced by IL, vector L, so that they're moving. Okay, so that we have IL, which now is more appropriate for a wire. And L is the, as I said, the displacement in the direction of the wire, and it has magnitude of L, the length of the wire. So we have IL cross B, and that gives us the magnetic force on a current carrying wire. So let's look at that a little bit further. All right. So we had FB equals IL cross B. So this is the cross product, the current, which is a scalar quantity, multiplied by the cross product of vectors L and B, the magnetic field. And so we can write this in magnitude form. The magnitude of the magnetic force will be ILB sine theta. And if we use this magnitude definition, then we know that the theta there is the angle between L and B. So this is the angle between L, which is in the direction of the current in the wire, and the magnetic field. So this looks very similar to what we saw for moving charges. This means that since we have sine theta and it's a cross product, if the current is parallel to the magnetic field, the magnetic will have sine of 0 and the magnetic field will not exert a force on that wire. So it has to be angled so that there's at least some component of that L vector that's perpendicular to the magnetic field in order for the wire to experience a force. So that gives us the magnitude. This is the magnetic force in newtons. Then we have current in amperes. L would be length in meters. And then our B is, of course, the magnetic field strength. In Tesla units of magnetic field. Okay, so if we use that magnitude form, in order to find the magnitude of the force, we need the direction. And the direction will come from the right-hand rule. The right-hand rule is essentially the same as we use for a current, because now when we place our fingers in the direction of the moving charge is in the direction of the current. So our first step is going to be place your fingers in the direction of the moving charge, so in the direction of the current, and then turn that vector, that's your L vector, turn it into the magnetic field. So fingers in direction of current, curl them towards the magnetic field, and the direction of the magnetic force will be the direction that your thumb naturally points. So let's do it on this diagram I have. This is I, current, so I want my fingers to be in the direction of the current. And then I'm going to curl them. This is into the page, so I'm going to curl them into the page, and then my thumb is naturally pointing to the left. So the magnetic force in that case would be directed towards the left. So I'll just pause for a second and get some more examples up that we can try. Okay, so just two more examples here, but you can refer to the video on the force on moving charges, since the right-hand rule is essentially the same. Okay, so if we look at A, we want to put our fingers in the direction of the current. Oh, it's out of the page this time, so something like this. And then I'm going to curl my fingers in the direction of the magnetic field. To do this, you can turn your hand any way you want so that your fingers are still pointing out of the page. So out of the page, I'm going to turn it like this and then curl them to the left. So that way, so I get up. I'll get my red marker. Okay, up is FB. So also notice or remember that this is a cross product. So it means that our magnetic force vector always has to be both perpendicular to both the magnetic field and the current. So if this is to the left and this is into the page or out of the page in that dimension, we only have up and down as our options. Okay, and then this one, part B, current is going to the right, and then I want to curl my hand out of the page, and that makes the magnetic force down. So again, fingers in the direction of the current, and then you can turn them how you need to, so that you can curl your fingers in the right direction and you get the direction of the magnetic force. And of course, if we had the current in the same dimension as the magnetic field, so parallel or anti-parallel, there would be no magnetic force exerted on the wire. But all right, let's do example 7. Okay, so a horizontal power line of length 58 meters carries a current of 2.2 kiloamps northward as shown. The Earth's magnetic field at this location has a magnitude of 5 times 10 to the negative 5 Tesla. The field at this location is directed towards the north at an angle of 65 degrees below the power line. Find the direction and the magnitude of the magnetic force on the power line. How would this situation be different if the power line was situated at Earth's equator? Okay, so have a look at the board. I've sketched out the situation and written the known information. We have the length, 58 meters, 2.2 kiloamps for the current, and the magnetic field, 5 times 10 to the negative 5 Tesla. Okay, and so this is the current in the wire, and they've said that the current in the wire is north. So if we're drawing it like this, then this is north, this direction. So south has to be the opposite direction, and then if you picture this as the 2D plane above the surface of the Earth, if that's north, then east has to be this way in the plane, which is out of the page, and west has to be into the page. And then the magnetic field is 65 degrees below the horizontal in the downward direction. Okay, so we put our fingers in the direction of the current. So part A, we're looking for the direction. Curl it down towards the magnetic field, and only the perpendicular component would exert a force. So essentially, we are just curling our fingers straight down there. Okay, so current, curl down towards the field, and I get into the page, which is in the west direction. Okay, so it experiences a westward force due to the magnetic field, and we can plug it in. So then our magnetic force on the wire is ILB sine theta to find the magnitude. So 2.2 times 10 to the 3 amps, 58 meters, 5 times 10 to the negative 5 Tesla, and then sine of 65 degrees to give me a magnetic force of 5.78 newtons. Notice that that is actually very small compared to gravity on the wire, which would be greater, and any other forces that would be significant on the wire. Okay, so also the last part of the question asks us if, what if this was closer to the equator, how would this change? And really what would change near the equator is the direction of these magnetic field lines. So closer to the equator, the magnetic field is directed closer to north. So they would move up this way and the angle would get smaller. They would be closer to the direction in the wire. And here, if this angle was smaller, then we would end up with a smaller magnetic force on the wire. So overall, that's really it. It would still be west if it was present, but it would be much smaller than the magnetic force on the wire here. Okay, let's look at the next example. Okay, example 8. The 20 by 35 centimeter rectangular circuit shown in the figure, which I'll draw on the board in a second, is hinged along the side AB. It carries a clockwise 5 amp current and is located in a uniform 1.2 Tesla magnetic field oriented perpendicular to 2 of its sides. Determine the direction and magnitude of the force exerted by the field on each sides of the circuit. Okay, so if you look at the board, it looks something like this. We have this current loop, it's hinged here, and then we have BC, A to B, B to C, C to D, and the current is 5 amps in the loop. Okay, so if we look at calculating the force on this loop, we're going to use F equals ILB sine theta. So let's look at what theta would be on each side of the wire. Notice that for B to C and for lengths A to D, so this line and this one, they are parallel and anti-parallel to the magnetic field. That means that the magnetic field will exert no force, will have sine of 0 or sine of 180, and we'll get 0 here. So the magnetic force is 0 along these two loops of the wire. There's no magnetic force there. Okay, and then we can calculate A to B and C to D. So we'll have F. Let's do A to B first. A to B is our current 5 amps times the length on that side, which is 0.2 meters, and then 1.2 Tesla sine. In this case, when it's going up, we have sine of 90, so it's exactly perpendicular to that field. And that gives me a value of 1.2 newtons. All right, and then, so if we look at the right-hand rule to find the direction, our fingers are in the direction of the current, and then curling towards the magnetic field, which is this way, and I get into the page at that point. Let's write that, into the page. Okay, and now over here, if I put my fingers in the direction of the current in the wire and then curl them here, oh, maybe it's better from this side. Let's see, put the fingers in the direction of the wire and then turn them to curl. There we go. So down and then curling, and I get out of the page. Okay, C to D. So everything will be the same except the direction, because we still have 5 amps, 0.2 meters for the length, and 1.2 Tesla. So this is a really interesting application. What we find is that there's 0 force on either side of this current loop on these horizontal sides, and on the vertical sides we have that the forces are in opposite directions. So an important result here is that the net force on a closed loop of current in a uniform magnetic field is equal to 0. So we'll always find this, that the net force overall will equal 0. But if you think about it, we had a force from A to B that was directed into the page, so pushing it this way, and from C to D, it's pushing it out of the page the other way. So if you picture this, maybe if this was free to move, I think it's hinged, but if it was free to move, we would see it turning this way. This would be pushed into the page and this was out, and we would get a rotation. So this is a very important application because the torque is non-zero. So however, the net torque is not 0. And we haven't looked at torque yet, but it's coming in the next module. And this torque means that there will be a rotation. So there will be a rotation of this closed loop of current in the magnetic field. And this would, as it rotates, the values of the forces and the torque would change. But it is the principle behind many applications, and I'll link some videos to some applications. One of them is a DC motor, and a simple DC motor would send current through a loop of wire in a uniform magnetic field, allow it to rotate, and then it has a switch that would switch the current halfway through to allow that torque to keep moving in the same direction, so that it doesn't end up stuck at the top. So the current's constantly flipping direction so that the rotor keeps on moving in a DC circuit. But I will post a video to that, and let me know if you have any questions.